Hello everyone. In this video, I'm going to go over the ideas of catalysis and how rate constants and activation energy really play a role in what is catalysis. Now, catalysis happens in a lot of ways and in a lot of systems. There are metal catalysts, there are enzyme catalysts, there are lots of different types of catalysts. And I'm calling this a bonus because this really isn't covered thoroughly in your textbook. There's a little bit in chapter 14, but we're going to go into it a little more generally here because we've been talking about activation energies and rate constants, and I kind of wanted to give you an application before we dove too much deeper into these ideas of kinetics. Okay, so this is sort of the view that we give in general chemistry. We say that when we add a catalyst, we lower the activation energy of the reaction. And so what this means is that when we are working with a catalyst, we have a smaller activation energy than when we are not working with a catalyst. And so the result of lowering the activation energy using a catalyst is that the reactions speed up. Now notice between using a catalyst and not using a catalyst, our delta H of our reaction stays the same. So that means that the energy between the reactants and the products stay the same because remember that this delta H is a state function, and so we're starting in the same spot and we're ending in the same spot. But the pathway that we take to get there changes. Another key thing with catalysts is that they are not a reactant or a product. And so that means that they are not used up or changed or created during the reaction. Instead, they're just used. Now, that's the Gen Chem view. The P-Chem view thinks about these reaction surfaces a bit more. And so I pulled a reaction surface from a fairly complicated reaction. And this is working to illustrate a point. Okay. I'm not going to go into the details of this reaction surface. So let's say that we start here. And we wanted to get to this minimum energy down here. And the reaction pathway could require us to go through this transition state before lowering down. If we were to use a catalyst, what happens is not that we change the surface. Instead, we create an alternative pathway. And that alternative pathway is also going to have activation energy. So maybe we come to a point over here before we go down. So what this looks like in 2 dimensions is that in blue, well, we have our reactants, we have our products. Our uncatalyzed route involves a very specific pathway. It has a transition state and an activation energy. When we add the catalyst, what ends up happening is that we create a different pathway or a different route to getting between the reactants and products. And so many times that's a multi-step sort of process where the activation energy, the biggest hump, is smaller than whenever we would go about this in a one-step sort of direction. And so in this diagram, the green is going to be uncatalyzed and the blue is going to be catalyzed. Whoops, I did that backwards. Ignore me. The blue is going to be uncatalyzed and the green is the catalyzed. So what does this look like mathematically? Well, it turns out that the only things that are changing are this rate constant and this activation energy, assuming that we're keeping the temperature constant. We can assume most of the time that this pre-exponential factor stays constant because really we are keeping everything the same about the collisions between the reactants and products. We are instead opening up an alternative pathway through the potential energy surface. So we can write this in the linearized form as well. So experimentally, what we end up doing to figure out the difference between the activation energy of the catalyzed system and the uncatalyzed system is that we measure the rates of the reaction with the catalyst and without the catalyst, and we find the activation energy for one of them. Usually that's it's going to be one of them. It can be either the catalyzed system or the uncatalyzed system. Sometimes finding the activation energy of the catalyzed system would be a faster sort of process because that reaction is going to go faster. But nevertheless, if we know three of these terms, whichever three we happen to know, what we can do is we can find the ratio of these rate constants and algebraically allow us to solve for the other missing piece. And so really this comes down to if we know three of the four variables, we can find the fourth algebraically. And it becomes just a process of rearranging these equations when we take the ratio of the catalyzed divided by the uncatalyzed.